A faint traveler moves through the deep interstellar dark far beyond the glow of any single star. It drifts within a sea of thin gas and scattered dust, its surface locked in ancient cold. Frozen layers of ice and rock record the light of a forgotten birthplace somewhere among the spiral arms of the galaxy where other suns rise and set on distant worlds. The object is small by the standards of planets, but large by the standards of wandering stones. It carries a slow spin, turning again and again in the dark, its axis tipped at some quiet angle that changes only under the faint touch of passing starlight. Each rotation exposes a different patch of surface to the thin rain of high-energy particles that fills interstellar space. Over time, these particles harden the outermost skin into a dark shell, a crust of altered material that hides fresher ice underneath. No nearby star pulls it strongly. No planet offers a close pass. It simply continues. The galaxy around it moves in long cycles. Stars orbit the galactic center star, forming regions light up and then fade, and spiral arms drift like slow waves. The traveler crosses unseen boundaries in the magnetic field of the galaxy and slips through faint wisps of gas between the stars, but it remains the same. Its path is set by the sum of tiny pushes and pulls from encounters long past when it was first flung out of its home system. Perhaps it brushed against a giant planet in that earlier time, or passed through a crowded region where multiple bodies danced under the pull of gravity until one was cast away. The traveler is no longer bound to any star. Eventually, the immense orbit of the Sun around the galaxy carries the heliosphere into the region where the object moves. The heliosphere is a vast bubble blown by the solar wind, a stream of charged particles flowing outward from the Sun. At its boundary, the pressure of this wind balances the pressure of the interstellar medium. Beyond that boundary, the traveler has wandered for ages. Now slowly and without any sign, it begins to feel the distant pull of a new star. This change is almost imperceptible at first. A tiny acceleration nudges the orbit, turning what was once a straight path into a gentle curve. The object still lies far beyond the known planets, immersed in a night that looks the same in all directions, but a small difference begins to grow. The Sun, still only one star among many, becomes slightly brighter than the others. The traveler's trajectory now bends inward toward the heart of a new system. As it approaches the outer edge of the heliosphere, the object meets the oncoming solar wind. Charged particles brush past its surface and begin to erode the most delicate grains of dust that have rested there for eons. The change is subtle. There is no sudden flash, no violent shock. Yet the local environment is no longer purely interstellar. The direction of the background wind becomes more ordered, pointing outward from the Sun, and the magnetic field gains a preferred orientation defined by the star at the center. Deep inside, the object cold remains. The bulk of its interior still sits at temperatures unchanged for countless ages. The outer layers, however, slowly adjust. With every step inward, the sunlight grows stronger. At first, it is no more than a gentle glow. Then, over a long interval that spans many months, the intensity climbs. Spectra taken from far away will later show the first hints of activity, a thin veil of gas surrounding an otherwise point-like nucleus. For now, the change exists only as a widening envelope of molecules and dust grains drifting away from the surface. In that distant region, the Sun is still no more than a bright star, yet its influence becomes the dominant guide of motion. The object now shares space with the loosely bound icy bodies that outline the farthest reaches of the solar family, though it does not belong to their ancient reservoir. It passes through unseen lanes of comets that have never fallen inward, and through the outskirts of paths traced by long-period visitors that once did. Its own path remains distinct, marked by an incoming speed that quietly announces a different origin. Surveys designed to watch the sky for moving points of light continue their patient work. Wide-field cameras sweep across star fields night after night, while software compares fresh images to older frames. The traveler is not yet among the catalogued objects tracked by the Minor Planet Center, nor in the lists watched by the International Asteroid Warning Network. Still, it moves steadily closer, its new path toward the Sun already fixed by events long past. The inner planets continue in their regular orbits, unaware of the distant visitor sliding toward their domain. In the months to come, sensitive detectors will measure its motion against background stars and find that it does not follow the usual pattern of a body born in the solar system. Its incoming speed will be higher than any long-period comet, and no amount of backward integration of its orbit will lead to the remote reservoir known as the Oort cloud. Those recognitions lie ahead. For the moment, the object is simply a wanderer crossing an invisible threshold, leaving the pure dark of interstellar space and entering the faint outer glow of the heliosphere, where sunlight and solar wind begin to write new layers of history onto an ancient surface. On a clear night above a volcanic island in the Pacific, a wide-field survey telescope begins its regular sweep of the sky. Its camera records long, shallow exposures, each frame filled with thousands of stars scattered across the sensor like grains of light. The images move silently into a waiting archive where software compares them to previous nights and to carefully prepared maps of known objects. Among these familiar points, one speck does not behave as expected. It shifts slightly more between exposures than nearby stars, and not in a way that matches the motion of a known asteroid or a routine comet. The difference is small, just a subtle displacement across the grid of pixels, barely noticeable to the human eye. Yet the automated system is designed to notice just such changes. It marks a speck, assigns a temporary designation, and sends a quiet alert forward into the network of planetary observers. The information travels to the clearinghouse of the Minor Planet Center, where positions from observatories around the world are gathered. Each reported coordinate links a moment in time to a tiny patch of sky, and with every additional measurement, the emerging path of the object becomes clearer. At first, the orbit solution is uncertain, a broad family of possible curves that could describe the same faint trail. With more data points, these possibilities narrow. Astrometry, the careful art of measuring positions, now shapes the story. Observers in different longitudes add follow-up measurements, timing their exposures so that the object appears at varying angles against the fixed star field. The Earth rotates beneath the sky, providing a gentle baseline for parallax, and over several nights, the changing geometry allows more precise determination of motion. The computed orbit refuses to settle into the pattern of a returning long-period comet, and it does not point back toward the distant spherical reservoir of the Oort cloud. Instead, the path suggests an object arriving from far beyond any known family. The apparent speed at great distance is higher than that of a body loosely bound to the Sun. When analysts project the orbit backward past the present epoch and into the distant past, the curve does not loop into a long ellipse. It stretches outward, becoming a nearly straight line that never quite closes. The best solution describes a track that begins in interstellar space and simply passes through the solar system on its way elsewhere, slowed and bent but never captured. The survey team that first recorded the object continues to watch. Night after night, as weather and scheduling allow, the telescope returns to the right ascension and declination, where the wanderer is predicted to appear. Sometimes thin cloud veils the sky and no new data arrive. Sometimes the object sits too low near the horizon or too close to the bright moon for clean detection. On other nights, the seeing is crisp and the point stands out just enough above the background noise to be measured again with modest uncertainty. Gradually, the quiet label of a temporary survey designation gives way to a more enduring name. The object joins the short list of known interstellar visitors and acquires a working identity that links it to the survey project that first noticed its unusual path. In internal notes and planning documents, many simply begin to call it Atlas III, a reminder of both its discovery and its place in the growing sequence of interstellar objects. At these early distances, the object shows only the barest hint of a coma, a softening of its point-like appearance into a tiny, unresolved disk. Photometry indicates a slight increase in brightness as it moves inward, consistent with the gentle awakening of surface ices under slowly rising sunlight. There is no dramatic tail, no sweeping fan of dust easily visible in small telescopes, only a suggestion that some gas is beginning to escape from the darkened crust. Astronomers allocate observing time on larger instruments to refine the measurements. Medium-sized telescopes with narrower fields but greater sensitivity examine the region around Atlas III, searching for any nearby fragments that might hint at an earlier breakup. None are obvious. Spectrographs attached to their focus gather the feeble light, spreading it into bands of color that may reveal the presence of common cometary molecules. The signal is faint, barely above the background, and early spectra are cautious in their interpretation. Coordination across the International Asteroid Warning Network and related groups ensures that the object remains on nightly planning lists. Although its trajectory poses no hazard to the planets, its interstellar origin makes it a priority. Ephemerides or updated charts are prepared, and software at major observatories incorporates its expected position into automated schedules. The object becomes another line in long tables of targets, yet the awareness grows that this is something rare. As the weeks pass, the curvature of the orbit grows more apparent. The sun's gravity continues to bend the path, guiding the visitor toward a perihelion that will carry it just inside the orbit of Mars. Simulations trace the future motion of Atlas III, showing its approach swing around the sun and eventual escape back into the dark. All of this appears routine in the equations, another test particle following the rules of celestial mechanics. Within those same calculations, however, lie the seeds of later surprise because the models assume that the object behaves as an ordinary comet. For now, the first faint points of light on survey images tell only a simple tale. A small body from another star system has come close enough to be seen. Its motion does not fit the patterns of local families, and its steady inward glide invites attention. The interstellar traveler that once moved unnoticed through the deep galactic night has acquired coordinates, a name in shared databases, and a growing ring of observers who will follow it from this quiet beginning through far more active stages yet to unfold. As the days of observation accumulate, the scattered measurements of Atlas III begin to form a coherent path. Each reported position is like a small marker placed on an invisible curve, and orbital computers at several centers now draw that curve again and again, refining it with every new point. The initial wide fan of possible trajectories narrows into a single elegant arc, one that links the inner solar system to the vastness beyond. Analysts examine the derived orbit with practiced attention. Standard routines first attempt to fit the path into familiar families. They test whether the object could be a long-period comet returning from the distant reservoir surrounding the Sun, or an extreme member of the cloud of icy bodies that sometimes send visitors plunging inward after gentle gravitational nudges. The results remain stubborn. Each time the algorithms try to anchor the orbit to a bound ellipse, the fit resists, and the residuals between prediction and measurement stay larger than expected. Gradually, a different picture emerges. The best-fitting solution is not an ellipse at all, but a hyperbola, a path corresponding to a body that arrives from outside the sun's long reach and departs again after a single swing. The incoming speed at great distance, called the hyperbolic excess speed, remains greater than the value that could belong to any comet loosely tied to the solar system. Atlas III is confirmed as an interstellar object, another member of a tiny group that includes only a handful of known examples. Attention then shifts to the orientation of the orbit. The inclination which describes the tilt of the path relative to the flat plane traced by the planets settles at a value only a few degrees away from that plane. The object approaches on a trajectory that lies almost within the ecliptic, yet it moves in the opposite direction to the planets, a retrograde arrival that threads the crowded region of planetary orbits from the other side. This combination of near alignment and opposite motion feels both natural and quietly remarkable. Visualizations help to make this more intuitive. On screens in observatories and research offices, the inner solar system appears as a set of nested ellipses, with Mercury, Venus, Earth, and Mars circling the Sun in the same direction along a common plane. Into this familiar arrangement, a pale line is drawn to represent the track of Atlas III. It slices through the planetary ring like a thin cord laid almost flat on a spinning disk, but it runs against the prevailing flow, crossing the paths of planets that will always have moved past that point by the time the object arrives. Dynamicists ask whether this geometry could be the result of random sampling from all possible orientations. They note that an interstellar object can, in principle, arrive from any direction tilted at any angle with any sense of motion. The fact that Atlas III arrives so nearly within the ecliptic plane, yet on a retrograde course, becomes a topic of quiet discussion. The probability of such an alignment is small but not vanishing. It sits in a range where the mind begins to wonder whether chance alone is responsible without yet demanding more exotic explanations. Further orbital refinements incorporate subtle gravitational influences from the planets. Jupiter, in particular, with its great mass, contributes a measurable tug as the object passes through its realm. Simulations run forward and backward in time, following the trajectory through the changing configuration of the solar system. They show that the visitor was not strongly deflected by any planet before entering the inner regions, nor will it experience a close encounter that might significantly alter its outbound course. The path is shaped primarily by the Sun itself. The orbit solution also allows researchers to trace the object's motion relative to the local standard of rest, a reference frame that approximates the average motion of stars in the solar neighborhood. Earlier interstellar visitors displayed interesting relationships to this frame, some appearing unusually slow relative to nearby stars. In the case of Atlas III, the derived motion seems more typical, consistent with the random ejection of a body from a distant planetary system sometime in the broad history of the galaxy. Even in this ordinariness, the precise configuration of its passage remains uniquely its own. At planning meetings, teams responsible for different observatories study ephemerides that now extend months into the future. These tables list predicted positions, brightness estimates, and sunward and anti-sunward angles, helping to determine when the object will be most accessible. The retrograde near ecliptic orbit means that Atlas III will spend significant time in regions of the sky near the Sun as seen from Earth, and therefore some portions of its trajectory will be hidden in glare. Other periods, however, will offer favorable elongations and allow deep imaging. One particularly interesting interval arises when the object's path carries it near the orbit of Mars. Calculations show that Mars will pass within a modest distance of the visitor, not close enough for a dramatic encounter, but near enough that instruments already in orbit around the planet could obtain valuable side views. The high-resolution camera aboard a long-lived Mars orbiter is identified as a candidate for such observations, and preliminary schedules note the dates when the visitor will be within range of that instrument's narrow field. As more data refine the orbit, attention turns to the small deviations that may signal non-gravitational forces. Outgassing from a comet can act like tiny thrusters, altering its path slightly compared to that of an inert rock. These effects are usually modeled with simple empirical terms that describe how sublimating gas exerts a recoil. For the moment, the astrometric record is not yet long enough and the activity not yet strong enough for these forces to be clearly separated from measurement uncertainties. Still, teams begin to watch for patterns that might hint at later surprises. Through all of this, the object itself continues its silent fall inward, oblivious to the lines drawn in computers and the numbers printed in tables. It follows the path set by its initial conditions and by the steady pull of the sun. The tracing of that path from afar, however, turns a nameless wanderer into a known traveler. Its hyperbolic orbit, its near alignment with the planetary plane, and its retrograde glide together form a quiet signature, a combination of characteristics that will later anchor deeper questions about what kind of body moves so precisely through the heart of the solar system and why it puts on such a remarkable display when it draws near to the sun. As Atlas III continues inward, the light of the sun grows steadily stronger across its mottled surface. The object now travels within the realm of the giant planets crossing orbits that have traced their paths for billions of years. None of these worlds lies close enough for a direct encounter yet. Their combined gravity adds a slight curvature to the visitor's already bent path, tuning the details of its journey toward the inner system. At these distances, the interstellar traveler begins to develop a more noticeable coma. Sunlight that once was no more than a distant glimmer now carries enough warmth to reach beneath the altered crust. Pockets of ancient ice sealed for ages behind layers of darkened material start to sublime. Molecules of water, carbon dioxide, and other volatile compounds slip free from the surface and drift outward into space. Dust grains once embedded in the ice are released and carried along, forming a thin, expanding envelope around the nucleus. To telescopes on Earth and in orbit, the point of light that once resembled a star now appears slightly softened. High-resolution images reveal a faint brightening around the nucleus, an unresolved glow that confirms the presence of a coma. Photometric measurements show a gentle increase in brightness in step with the decreasing distance from the sun, consistent with the behavior of an awakening comet. Nothing in these early changes hints at the extremes that will later emerge. Modelers take these observations and fold them into their simulations. They assign reasonable values for the thermal properties of the surface, the depth of volatile layers, and the likely distribution of active patches across the nucleus. With these ingredients, they project how the coma and any tails should evolve as Atlas III moves closer to the sun. The results are unremarkable. The expected outgassing is modest, the mass loss within the range of many comets that have been seen before, and the predicted jets are short compared with the immense structures that will eventually be recorded. These models shape expectations. Observers plan their campaigns around the idea of a relatively quiet interstellar comet that will brighten near perihelion, develop a modest tail, and then fade as it recedes. This alone would be a valuable case study, adding a more typical member to the very small sample of known interstellar objects. After the unusual behavior of earlier visitors, many welcome the prospect of a calmer example to help define what is ordinary in this new class. During this period, the orbit brings Atlas III gradually closer to the plane of the inner planets. Its path intersects the broad zone in which small bodies, dust, and human spacecraft all move under the sun's pull. Yet the distances involved remain large. The object stays far from the Earth and the other terrestrial planets, and no collision scenarios arise in planetary defense calculations. The Planetary Defense Coordination Office and its partners continue to track the object, but the focus remains scientific rather than protective. The interstellar visitor passes the distance of Jupiter's orbit and continues inward. The solar wind grows denser and the background of charged particles becomes more intense. The thin coma interacts with this flowing plasma, shaping the earliest versions of a tail that extends away from the sun. The solar magnetic field guides charged particles along curved lines, bending the tail into a gentle arc that points roughly opposite the sun. As the object draws nearer, its motion across the sky speeds up. Observatories coordinate to ensure coverage as it moves from one constellation into another, tracing a path that on charts appears as a gentle curve among the stars. Early morning and late evening windows are used to catch it at favorable angles away from the sun's glare. In the midst of passing satellite trails, the ancient visitor continues to slip across each frame, following a course set long before any human artifacts were launched. Amid the gathering data, nothing yet stands out as extraordinary. The coma's size, the rate of brightening, and the early tail length all fall within the broad envelope of known cometary behavior. Papers and conference talks describe Atlas III as an interstellar comet of apparently standard activity, noteworthy mainly for its origin outside the solar system and its convenient passage through the inner regions where instruments can study it. The tone is measured, the language cautious, reflecting the still limited set of observations. Behind the scenes, however, a few modest curiosities emerge. Preliminary attempts to include non-gravitational accelerations in the orbital solution show faint hints of recoil forces that seem slightly stronger than the observed activity would suggest. The uncertainties remain large and no firm conclusion can be drawn, but some dynamicists mark these results for later attention. The possibility that outgassing might not fully account for the motion becomes an item on a quiet list of questions to revisit once more. Precise astrometry is available after the object rounds the sun. For the moment, the narrative remains simple. A dark, compact body from another star system has entered the inner solar system. It is warming under increasing sunlight, shedding gas and dust into a developing coma and tail, and following a hyperbolic path that will carry it near the orbit of Mars before sending it back outward. Observers refine their plans and adjust their models in the expectation of a modest, instructive, and largely conventional display. The interstellar traveler continues to drift inward, giving no outward sign that it is about to depart so sharply from those expectations when it reaches the critical region near perihelion. As Atlas III approaches the inner regions of the solar system, its path across the sky bends steadily closer to the sun as seen from Earth. Each night, the elongation, the angle between the object and the sun shrinks a little more. Observers who have followed it from dark, high-altitude sites watch the window of visibility narrow. The interstellar traveler is brighter now, its coma more fully developed, yet it is paradoxically becoming harder to see as twilight and scattered sunlight begin to dominate the sky near its position. Tracking an object so close to the solar limb risks both instrumental safety and degraded data, so schedules begin to thin. Solar conjunction will soon place Atlas III so near the sun in the sky that Earth-based observatories must pause their work. In anticipation, teams condense their campaigns into the final weeks before the gap. High-resolution images from major observatories map the brightness around the nucleus, searching for asymmetries that might hint at discrete jets or active regions. Spectrographs collect photons across a broad range of wavelengths, building up signal for faint molecular lines released from the warming surface. The data show steady growth rather than sudden change. The coma extends farther from the nucleus than before, but not yet to extraordinary scales. Dust grains scatter sunlight, producing a gentle brightening that follows expectations from simple thermal models. Gas emissions strengthen as more volatile material sublimates, and the early tail lengthens modestly in the antisolar direction. Each new spectrum and image reinforces the picture of a fairly ordinary, if interstellar, comet. At the same time, conditions around the object are becoming more intense. The solar irradiance at its distance climbs rapidly as the orbit carries it inward. Radiant energy penetrates more deeply into the interior, melting and refreezing pockets of ice, opening fractures and raising internal pressures. Thermal contrasts between sunlit and shadowed regions sharpen as the spin of the nucleus cycles surfaces from darkness into strong daylight and back again. Inside the solid body, stresses build quietly out of direct view. Earth-based observers cannot see these internal changes, and soon even indirect clues begin to fade. The object sinks into the bright evening sky, then into the narrow gap between the horizon and the sun where observations are almost impossible. A few attempts are made with coronagraphs and specialized daytime techniques, but the results are limited. Gradually, Atlas III passes into an observational blind spot. Elsewhere in the solar system, geometry offers a different opportunity. As the orbits of planets progress, a period arises when Atlas III passes relatively near Mars. Spacecraft in orbit, they're normally devoted to mapping the Martian surface and atmosphere, are briefly retasked. A high-resolution camera that usually inspects fine details on the terrain turns outward to image the passing interstellar visitor, capturing it from the side rather than almost head-on. During a short interval, frames record the visitor against the star field from this distinctive perspective. When the data are relayed back through deep space networks, they enter archives managed by agencies coping with reduced staffing. Calibration and public release are delayed. The side view of Atlas III during this critical phase exists, but for a time it remains unseen by most who study the object, a small store of unexamined structure at the very moment when activity may be changing most rapidly. Back near Earth, the conjunction deepens. For several weeks, the line of sight from ground-based observatories passes too close to the Sun for safe, effective tracking. Space-based solar observatories carry coronagraphs and heliospheric imagers that sometimes catch comets in their fields as they skim near the Sun. In the case of Atlas III, some of these instruments record faint traces of the developing tail, but their resolution and sensitivity are not suited to detailed structural studies. They provide context rather than fine detail, showing only that the object moves through the near-solar environment with rising activity. Within this interval of limited visibility, Atlas III reaches perihelion, its closest approach to the Sun. The solar flux on its surface attains a peak, internal temperatures rise and sublimation rates climb. Pre-existing fractures may widen into vents that feed narrow outflows, and deeper volatile reservoirs may suddenly connect to the surface. Under these conditions of maximum heating and stress, the jets that will later astonish observers likely first extend to their remarkable scales and complex geometry. Because the full structure of these jets cannot be observed directly from Earth during conjunction, the period around perihelion becomes a gap in the detailed record. Models must carry the story across this blind span, guided by physics but lacking high-resolution images. Researchers draw on previous comets as templates, adjusting parameters to explore how activity might evolve when buried ice is newly exposed and mass loss rates spike. Their scenarios differ in detail, but agree that the most dramatic changes are likely to occur while direct sight is lost. When the orbital motion finally carries Atlas III away from the Sun as seen from Earth, the elongation begins to increase again. Slowly at first, then more rapidly, the object moves into evening skies, where the background is dark enough for renewed observations. Telescopes that had been unable to track it safely near the solar limb return to the predicted coordinates. In the weeks after conjunction, they find not the modestly active interstellar comet that earlier models had anticipated, but a visitor adorned with enormous, finely drawn jets that seem to have grown while hidden from view, turning the time of invisibility into a quiet hinge between ordinary behavior and something far more unusual. When Atlas III emerges from the glare of the sun as seen from Earth, the change in its appearance is immediate to those who compare new images with the quiet frames from earlier months. The first deep exposures taken after conjunction show a nucleus still unresolved as a point, but around it stretch structures larger and more intricate than most had expected. What was once a soft, nearly spherical coma has become a scaffold of narrow beams, threads of light that trace long paths through space. Two of these structures draw attention first. They seem to point almost directly toward the sun, an unusual orientation for features that resemble anti-tails. In most comets, dust tails stream away from the sun, carried outward by radiation pressure and the solar wind. In rare cases, the viewing geometry can make dust confined to the orbit plane appear as a sunward tail. In the case of Atlas III, the sunward jets are unusually straight and sharply defined, extending for nearly 1 million kilometers narrow compared with their reach, yet broad compared with the modest halo seen earlier. Analysts measure their extent by tracing brightness along the jets until it fades into the background. The result is a scale that dwarfs the earlier coma by roughly 3 orders of magnitude. The glowing envelope that the Hubble Space Telescope recorded months before now seems small when set beside these new structures. The difference becomes a quiet indicator of how strongly the activity has changed near perihelion, with material now reaching distances that earlier models never anticipated. A third beam adds further complexity. Instead of pointing toward the sun, it projects outward a collimated structure that stretches roughly 3 times as far as the sunward jets. Along its length, subtle variations in brightness suggest knots or changes in density, though the limited resolution leaves these features open to interpretation. The full span of this outward beam approaches several million kilometers a distance that, when translated into more familiar scales, rivals many times the separation between Earth and its moon. The size of these structures demands explanation. Sublimation-driven flows from comet surfaces at this kind of heliocentric distance typically reach speeds of only a few tenths of a kilometer per second. For gas and dust moving at such speeds to form jets of the observed length, the emission must persist for extended periods on the order of months without major interruption. Yet the earlier record suggests that Atlas III was relatively quiet until shortly before perihelion, showing modest activity and little hint of the outburst that now appears. Estimating the mass loss required to sustain these jets becomes an exercise in careful inference. By combining the measured brightness with assumptions about particle sizes, composition, and scattering properties, researchers derive approximate densities along the beams. From these, along with flow speeds constrained by the physics of the local environment, they calculate the rate at which material must be leaving the nucleus. The values that emerge are large, corresponding to tens of billions of tons per month for the most intense phases of activity, comparable in some estimates to the minimum mass of the nucleus itself. Such a rate implies that a substantial fraction of the object could in principle be lost over a relatively short interval. Either the mass of Atlas III is much larger than early assumptions suggested, or the current episode of extreme activity is brief, perhaps confined to a narrow window around perihelion when buried volatile reservoirs were suddenly exposed. Both possibilities are consistent with a natural comet undergoing an outburst, yet the extremity of the numbers nudges the imagination toward broader questions about internal structure and energy sources. Attention also turns to the way these jets interact with the solar wind. to maintain coherent sunward-directed structures against an outflow of charged particles moving hundreds of kilometers per second. The jets must carry notable momentum and pressure. In models where the solar wind would normally bend and disperse such features quickly, Atlas III seems instead to sustain them as though the balance between internal outflow and external forcing lies in an unusual regime. Some simulations suggest that dense dust-rich jets might resist disruption longer than gas-dominated ones, hinting that the composition of the outflow could play a crucial role. The timing of the change adds another layer of interest. Before conjunction, the visitor shows gentle activity. After conjunction, the jets have already reached enormous scales. The days surrounding perihelion, when direct imaging from Earth is most difficult, therefore appear to have been the stage on which the transition occurred. In that hidden interval, vents may have opened, layers may have collapsed, or interior pockets may have connected to the surface, turning a modest emitter into a source of finely directed flows. Through all of this, the tone of analysis remains measured. The extraordinary appearance of the jets is described in calm terms, their scales expressed in kilometers, and in comparisons to familiar distances, their energies estimated within ranges of uncertainty. Hypotheses begin with the established physics of sublimation, dust dynamics, and solar wind interaction, and only later open into soft speculation about whether more complex processes might be at work. The image of Atlas III has changed from a simple glowing point to a many-threaded structure, and with it, the understanding of what an interstellar visitor can do when it passes close to a star has deepened, leaving space for new questions that reach beyond the standard picture of cometary behavior. From the moment the first post-conjunction images circulate through the astronomical community, attention turns to the dynamics that could sustain structures as long and finely drawn as the jets of Atlas III. Twin beams appear to reach almost toward the Sun, while a third column stretches outward along the line away from the star. Together they sketch a delicate scaffold around an unresolved core, giving the interstellar visitor an outline more like a careful drawing than a simple cloud. Modelers return to the basics of comet physics. Sublimation, the direct transition from solid ice to gas, remains the standard engine for cometary activity. Sunlight warms a patch of surface ice molecules escape, and gas carries dust grains outward. On a rotating nucleus with uneven composition, some regions become more active than others, so jets form and curve as the nucleus spins, tracing spirals that can often be mapped back to discrete vents. Many comets have been seen to behave in this way, with graceful plumes that broaden and bend as they expand. The jets of Atlas III echo part of this picture, but stretch it into unfamiliar territory. Their length and straightness suggest flows that maintain coherence over distances where ordinary jets would diffuse into the background. The strongly sunward orientation of the twin beams adds further complexity. Sunward features and anti-tails have appeared in earlier comets, usually as perspective effects when dust confined to the orbital plane is seen from a particular angle. Here, the nearly ecliptic retrograde orbit certainly shapes the viewing geometry, yet the narrow, sharp beams encourage the idea that dense collimated streams genuinely exist. Numerical experiments explore how dust grains of different sizes respond to solar radiation pressure and the solar wind. Large grains with more mass and less exposed area per unit mass feel weaker push from light and plasma, and so remain closer to the original direction of flow. If Atlas III ejects an unusually high proportion of such large particles, the sunward beams could be massive streams of heavy grains that hang along the orbital plane, while the outward jet could be richer in gas and fine dust, more easily bent by the heliospheric environment. In this view, the overall structure arises from a combination of internal venting and external forces. Even with such adjustments, however, the implied mass loss remains striking. Flow speeds set by gas temperature and local conditions limit how quickly material can travel along the jets. Given these speeds and the observed lengths, the jets must have been fed for weeks or months. Integrating density along their paths leads to totals of material that reach tens of billions of tons over the most active periods. This in turn suggests either a nucleus far more massive than early brightness estimates implied, or a brief but intense phase in which a significant fraction of the body is removed. Astrometric teams fold this reality into their orbit solutions. With post-perihelion measurements added, they now include non-gravitational terms that represent the recoil from outgassing. The refined fits show small but measurable accelerations that cannot be attributed to gravity alone. The preferred solutions indicate that the net thrust does not cancel perfectly, nudging Atlas III in ways that slightly adjust its outbound course. The effect is subtle yet large enough to confirm that the jets are not just graceful ornaments but active forces sculpting the trajectory. These results invite comparison with earlier interstellar visitors. One of them displayed non-gravitational acceleration without obvious signs of a coma, leading to debates about exotic ices or unfamiliar driving mechanisms. Atlas III offers almost the mirror image, vigorous dramatic jets, whose intensity and organization challenge ordinary models while still clearly rooted in outgassing. Together, the small sample of known interstellar objects now spans a broader range of behaviors than anticipated, hinting that visitors from other star systems may be more diverse than local comets. Within this context, more speculative ideas are raised with care. Some researchers examine whether internal heat sources such as the slow decay of long-lived radioactive elements or latent chemical energy in complex mixtures might supplement sunlight and sustain high activity for longer than surface heating alone would allow. Others explore the possibility of extensive internal fractures or hollow regions that could funnel gas through narrow channels, naturally producing collimated jets without requiring exotic materials. In each case, the emphasis remains on stretching known physics rather than invoking wholly new principles. As weeks pass, observers notice that the jets, though persistent, are not entirely steady. Their brightness rises and falls, edges sharpen and soften, and the balance between sunward beams and outward columns shifts slightly with time. The basic pattern endures, yet within its small changes hint at a living, responsive system. Through all of this, Atlas III is regarded less as a violation of expectation than as an exacting test. Long-standing ideas about cometary outgassing, dust dynamics, and non-gravitational forces are applied in a regime of unusual intensity and geometry. The long sunward pointing jets and the extended outward beam become not only striking images but also boundary conditions for any theory that seeks to explain how an interstellar nucleus behaves when drawn very close to a star. In this calm analysis, the visitor appears as a rare but natural experiment, one that invites deeper thought about how familiar processes can combine to produce patterns that at first glance seem almost too precise to belong to a simple fragment of ice and rock that has traveled for ages between the stars. While Atlas III turns its face toward the sun, another world watches from a different vantage point. Mars, following its own broad ellipse, happens to pass within a modest distance of the interstellar visitor. Against the red planet's thin air and dusty plains, a long-lived spacecraft circles in a near-polar orbit, its instruments tuned for the study of Martian landscapes, but still capable of glancing outward when geometry permits. Among these instruments is a high-resolution camera designed to pick out boulders on crater rims and layers in ancient sediment, yet also able to resolve distant points of light into more than a single pixel. Mission planners on the ground examine the evolving ephemerides and recognize a narrow window. For a brief period, the line from Mars to Atlas III passes at an angle quite different from that available to Earth-based observers. Where telescopes near Earth see the interstellar comet almost along the direction of its jets, the camera at Mars can record a profile view side onto the developing structures. Commands are drafted to turn the spacecraft slightly away from its usual targets and to capture a sequence of images as the visitor passes through the field. At the appointed times, the orbiter obeys. During a span of hours spread over 2 Martian days, it pivots, stabilizes, and opens its shutter. The high-resolution camera takes frames in which Atlas III appears as a small, bright condensation surrounded by a faint extended region. From this vantage point, any jets, fans, or fragments will appear foreshortened in ways that complement the perspective from Earth. The data stored in onboard memory wait for scheduled transmission sessions when the spacecraft passes over relay antennas and beams its records across the gulf between Mars and Earth. Radio signals carrying those images join the steady flow of information from the Martian system. They arrive at deep space receiving stations and are routed to processing centers that calibrate and archive incoming data from many missions. Normally, such images would pass through a sequence of steps that correct for instrumental effects, assign precise pointing information, and prepare them for public release. Scientists on the instrument team would inspect the frames, verify quality, and issue notices that a rare side view of an interstellar visitor near perihelion is now available. This time, the timing coincides with a period of difficulty on the ground. Political disagreements in the nation that operates the Mars orbiter lead to a temporary shutdown of many government activities. The National Aeronautics and Space Administration, responsible for managing the mission and its data, enters a reduced operational state. Essential functions to protect spacecraft continue, but many routine tasks, including the full processing and release of new observations, slow or pause. Staff members who would normally tend the flow of images are furloughed, and projects that do not involve real-time safety are placed on hold. In this environment, the Atlas III images from Mars become part of a growing backlog. They are safely stored, preserved on servers, and in redundant systems. But their journey from raw data to fully processed, publicly accessible products is delayed. Requests from outside researchers for early access meet automated acknowledgments and polite explanations that normal operations will resume once funding is restored. The universe continues at its own pace while human institutions move in fits and starts. Within the wider astronomical community, awareness of the Mars side view spreads through conference talks, informal correspondence, and notes in planning documents. Orbit calculations show exactly when and how close the visitor passed to Mars, and mission status reports confirm that the high-resolution camera did in fact observe it. The knowledge that images exist but are not yet available becomes a quiet point of tension. Researchers who are refining models of the jets and searching for signs of fragmentation know that a lateral perspective taken just before or during the strongest outburst could reveal whether the nucleus remained intact or split into pieces. Some members of the scientific community and a few policymakers express concern that this delay comes at a particularly sensitive moment. The evolution of the jets is rapid. Each week after perihelion, the structures change as the object moves away from the Sun and activity begins to taper. The most valuable comparisons would link the profile view from Mars to nearly simultaneous observations from Earth, creating a three-dimensional picture of the outflows. With every passing day, the observations become less contemporaneous, and the chance to see the precise state of the system during its peak begins to fade. Discussions unfold in calm but pointed language. Advocates for open data note that images of a comet, even an interstellar one, do not pose security concerns. They argue that access to such information should not be entangled with broader political debates. Letters and public statements from scientists and interested legislators gently urge that at least this small subset of Mars data be moved forward in the pipeline as soon as staff return, so that the community can make full use of a rare and unrepeatable observation. Meanwhile, telescopes on Earth resume their own tracking as Atlas III emerges into darker evening skies. The jets are measured, mapped, and modeled in detail from this single vantage point. Spectrographs characterize the composition of the outflowing gas, while photometry tracks changes in overall brightness. The missing side view from Mars becomes an absence that scientists learn to work around using indirect methods to infer what the nucleus might look like in profile. Some simulate hypothetical fragment distributions and compare their projected signatures to the patterns seen from Earth, all the while aware that a direct image sits unseen in a distant archive. Months later, when institutional constraints ease, and more routine operations resume, those Mars images are finally processed and examined with care. They reveal a compact central condensation and asymmetric extensions consistent with strong jetting, though limitations in resolution and exposure time leave some questions open. For some, the delayed arrival of these frames underscores how fragile the chain can be between the moment when photons strike a detector in deep space and the moment when they inform collective understanding. Even in a field that often deals with timescales measured in millions of years, windows of hours or days can matter when phenomena change quickly. In retrospect, the sideways glance from Mars and the pause in its release become part of the story of Atlas III as surely as the jets themselves. The interstellar visitor has interacted not only with sunlight, dust, and the solar wind, but also with the structures of human activity that govern how observations are shared. The high-resolution camera aboard a distant orbiter has done its work faithfully, recording a brief encounter between an ancient wanderer and a modern robot circling a neighboring world. The images eventually enrich the record, yet the interval during which they were unseen leaves a faint imprint, a reminder that in the study of transient cosmic events, timing on Earth can be as significant as timing in space. As the geometry of the sky slowly changes, Atlas, 3 steps back from the sun's blinding vicinity. Evening by evening, the elongation grows, drawing the visitor away from the bright horizon and into darker regions where sensitive instruments can again follow its light. Observatories that had set the object aside during conjunction now return to the ephemerides and prepare their schedules. The interstellar traveler is no longer a near-invisible speck smothered by solar glare. It has become a structured source adorned with jets that reach far beyond the modest coma first recorded months before. On mountaintops beneath thin, cold air, large optical telescopes swing toward the coordinates calculated by orbital computers, their domes open with deliberate motion, exposing mirrors that have waded through days of stepwise tracking of other targets. Guiding systems lock onto nearby stars and long exposures begin. On the detectors, Atlas III appears once more, but the pattern around the nucleus is transformed. The 3 primary jets stretch out as elongated streaks across the field, their brightness gradually declining with distance from the center, but remaining detectable far from the core. Technicians and scientists inspect the raw frames with quiet concentration. Each image is calibrated to remove instrumental signatures, then combined with others taken in sequence. The resulting deep stacks reveal a multi-threaded structure that nearly fills the camera's field of view. The twin sunward-oriented jets remain sharply defined, cutting across the background like narrow bridges of dust and gas. The outward pointing column stands even longer and straighter than before its far reaches, fading softly into the darkness. Along all three beams, faint ripples hint at changes in emission or small waves imposed by the changing environment. Spectrographs now play a central role. Light from the region around the nucleus is guided into narrow slits stretched into spectra and recorded as bands of varying intensity. Within these bands, subtle features indicate the presence of water vapor, carbon-bearing molecules, and other species commonly found in cometary Comet. Further out along the jet's spectra reveal how the composition may vary with distance. In some areas, gas signatures weaken more rapidly than dust scattering, suggesting that large solid particles remain where lighter molecules have already dispersed. Polarimeters add another layer of information. By measuring the direction and degree of polarization of scattered sunlight, these instruments infer the sizes and surface properties of the dust grains that fill the jets in coma. Maps of polarization across the image show differences between the sunward beams, the outward column, and the diffuse halo. In the twin sunward jets, polarization patterns indicate a population of relatively large compact grains, consistent with the idea that heavy particles are less easily swept away by radiation pressure and solar wind. The outward jet, by contrast, shows stronger signs of finer dust, more responsive to the forces that shape the larger scale tail. Night after night, a global pattern of observations builds up. Telescopes in the southern hemisphere watch during their evening hours, then pass the task on to northern instruments as the Earth turns. Space-based observatories above the blurring effects of the atmosphere contribute higher contrast images and ultraviolet and infrared spectra that the ground cannot obtain. Together, these many eyes assemble a time series, a sequence of measurements that record the evolution of Atlas III's activity as it recedes from perihelion. The jets themselves become clocks of a kind. By comparing their observed lengths on different nights and factoring in the changing distance between the object, the Earth, and the Sun, researchers determine how rapidly the structures are growing or shrinking. Small shifts in direction are traced relative to background stars, revealing how the orientation of the jets responds to the rotation of the nucleus and to the changing flow of the solar wind. In some intervals, brightness knots appear to move outward along the beams, as though packets of denser material are traveling through the already established streams. Astrometrists continue to mark the nucleus position as precisely as possible on each new frame. Against the intricate background of jets in coma, they identify the central condensation and fit its location to subpixel accuracy. These points feed into the orbit determination process, allowing refined estimates of non-gravitational accelerations. As more post-perihelion data accumulate, the models begin to show clearer signs of sustained recoil forces. The direction and magnitude of these forces align broadly with the time-averaged pattern of jets, confirming that the dramatic visible structures are indeed responsible for the subtle reshaping of the object's trajectory. As Atlas III draws nearer to the Earth along its hyperbolic path, its apparent brightness increases despite the gradual decline in solar heating. The closer distance compensates for the slowly weakening activity, making the interstellar visitor accessible to a wider range of instruments, including smaller professional telescopes and advanced amateur setups. Careful observers with modest apertures under dark skies can record the faint outline of the main jets, especially the outward beam, while larger facilities continue to resolve finer detail near the nucleus. Throughout this phase, coordination remains essential. The International Asteroid Warning Network, the Minor Planet Center, and various regional consortia share ephemerides, observational priorities, and preliminary interpretations. Dedicated campaigns allocate time on the largest optical and infrared telescopes, as well as on radio arrays that listen for emissions from molecules in the coma. Each group approaches the visitor with its own tools and questions, yet their efforts all feed into a common picture of how this interstellar object behaves as it moves through the middle distances of the solar system. Even as data accumulate, the mood stays quietly reflective rather than urgent. Atlas III poses no threat to any planet, and its closest approach to Earth will still leave a wide margin measured in hundreds of millions of kilometers. The sense of importance arises not from hazard but from uniqueness. Observers know that the combination of interstellar origin near ecliptic retrograde orbit and extreme jet structures is unlikely to be duplicated soon. Each clear night during this window feels like a small, irreplaceable opportunity to add another piece to a puzzle that stretches from the deep past of a different star system to the transient present of its passage here. As the weeks progress, subtle changes in the jets become more apparent. Edges that were once razor-sharp begin to soften, and brightness along their lengths decreases. The outward column starts to fragment into a more diffuse tail, while the sunward beams become shorter and less intense. The coma grows more symmetrical again as the most active vents either exhaust their volatile reserves or retreat beneath a thickening mantle of redeposited dust. Through all of this, the steady gaze of telescopes in the evening skies records the fading spectacle, ensuring that the remarkable geometry of Atlas III during its brightest, most structured phase is preserved in a rich record of photons gathered from many sites across the Earth. With the return of regular astrometric measurements after conjunction, the orbit of Atlas III becomes not only a path to predict on the sky, but also a subtle record of forces at work near the nucleus. Each position marked against the background stars carries within it the sum of gravity from the sun and planets and any additional pushes from escaping gas and dust. Over weeks and months, small deviations between the observed locations and the positions predicted by a purely gravitational model begin to stand out faint signatures of influences beyond simple attraction. Astrometrists approach these discrepancies with care. They examine possible sources of error in the observations, checking timing, calibration, and the influence of the surrounding coma on centroid measurements. Frames taken under poor seeing or at low altitude are weighted less heavily or set aside. What remains is a set of positions that agree closely with one another yet consistently differ from a gravity-only trajectory by tiny but measurable amounts. The pattern of residuals points toward a gentle, persistent acceleration that appears to act roughly along the direction of the strongest jets. Standard comet models include empirical terms to describe such forces. These non-gravitational parameters are usually expressed through simple functions that relate the strength of the recoil to the distance from the sun, assuming that the outgassing depends mainly on how much sunlight reaches the nucleus. When these terms are added to the equations of motion for Atlas III and adjusted to fit the data, the match improves noticeably. The refined orbit passes closer to each measured point and the residuals shrink. The visitor is now understood as a body whose trajectory reflects both the pull of the solar system and the thrust of its own escaping material. What distinguishes Atlas III is not the mere presence of non-gravitational acceleration, which is common among active comets, but its combination with the extraordinary structure of the jets and the estimates of mass loss implied by those structures. The directionality of the measured acceleration averaged over time aligns with the overall pattern of the jets mapped in images. Regions where the jets appear more intense correspond to intervals when the non-gravitational terms must be stronger to reproduce the positions. In effect, the orbit solution becomes another way of sensing the jets, reading their influence not in light but in motion. Dynamicists use these results to infer more about the nucleus itself. If the jets are concentrated in discrete areas, then the net thrust depends on how those areas are distributed across the surface and how the nucleus is oriented as it spins. A roughly isotropic pattern of activity would tend to cancel out over a rotation, producing little net acceleration. The clear sustained signal in the orbit suggests that Atlas III's activity is uneven with certain regions dominating the outflow. This picture agrees with the imaging, which shows a few major beams rather than a uniform halo. From the strength of the non-gravitational acceleration and estimates of the mass loss rate, researchers can derive an effective ratio between the mass of the nucleus and the thrust of the jets. If the jets are as powerful as the visible structures imply, then either the nucleus must be relatively massive to avoid extreme acceleration, or the active phase must be short-lived. Calculations that treat the observed acceleration as a long-term average hint that the nucleus may have a diameter of several kilometers or more, placing Atlas III among the larger known interstellar visitors, and explaining how it can continue to shed vast quantities of material without disintegrating entirely. These inferences intersect with considerations of probability. In the small sample of confirmed interstellar objects, most have been markedly smaller with weaker activity or less dramatic signatures. To encounter a visitor as large and active as Atlas III so soon in the era of systematic sky surveys feels unlikely under some assumptions about the distribution of interstellar bodies. Statistical arguments explore how often an object of this scale should pass within range of Earth-based detection, and how long one would need to wait on average to see such a combination of mass activity and favorable geometry. The answers depend sensitively on how mass is apportioned across the population of interstellar fragments. If most of the material resides in large bodies, then a giant like Atlas III may be expected to appear at least occasionally, even within a relatively short observing window. If instead the mass is shared more evenly among objects of many sizes, then the appearance of a very large, strongly active visitor in the first handful of detections becomes more surprising. In either case, the existence of Atlas III pushes models of interstellar debris toward accommodating more massive, more energetic members than previous examples alone would have required. Within this frame, the non-gravitational acceleration becomes both a constraint and a clue. It confirms that the jets carry enough momentum to reshape the orbit slightly, yet not so much as to fling the object off its predicted course by large margins. It suggests that the internal structure of the nucleus can withstand strong localized stress without immediate total disruption. It supports the idea that activity is concentrated rather than uniform, and that these concentrated regions have been active for long enough to leave an imprint on the trajectory. At the same time, the motion of Atlas III does not reveal any abrupt discontinuous changes that would signal a sudden large-scale fragmentation or an impulsive event vastly different from outgassing. The orbit tracks smoothly through perihelion and into the outbound leg, modified by steady thrust rather than sharp kicks. Whatever processes produced the remarkable jets appear from this perspective to have acted continuously over many rotations and many days, even if they may have begun during a relatively brief interval near closest approach to the Sun. Some researchers, noting the smoothness of the accelerations and the precision of the jets, allow themselves gentle speculation about whether additional factors might be in play. They consider, for example, whether deeply buried pockets of volatile material could act in a coordinated way as the thermal wave from solar heating penetrates, turning on activity across multiple regions in a pattern set by the internal layout of fractures and voids. Others explore whether the orientation of the spin axis combined with the near ecliptic retrograde orbit might naturally favor the emergence of jets that appear finely aligned when projected onto the sky. In every case, the guiding principle remains the same. The forces beyond simple gravity must be accounted for in a way that matches both the visible structures and the measured orbit. The jets, the non-gravitational parameters, and the long hyperbolic path through the solar system together form a single coherent story. Atlas III becomes a demonstration that even in the realm of interstellar wonders, the familiar interplay between sunlight sublimation and recoil can produce outcomes that initially seem improbable, yet still fit within an expanded, carefully tested understanding of what icy bodies can do when they fall briefly under the influence of a star. As observations of Atlas III deepen, attention turns inward toward the unseen interior that sustains its long, narrow jets. Images show beams emerging from a region smaller than any telescope can resolve a bright knot from which the structures seem to spring. Whether that knot hides a single coherent nucleus, a tight cluster of fragments, or a hollow shell becomes a central question, because each possibility would respond differently to the stresses of close solar passage and intense mass loss. Cometary science offers a few guiding patterns. Some nuclei visited by spacecraft prove to be rugged, consolidated bodies with cliffs and pits carved by repeated heating. Others fragment near the sun or under tidal forces, leaving chains of smaller pieces moving along nearly identical paths. For Atlas III, the extraordinary jets invite all of these analogies, yet fit none exactly. If the nucleus is largely solid, its self-gravity and internal strength might help it endure the intense outflow implied by the beams. Vent systems could cut deeply through the body, channeling gas from buried reservoirs toward a small number of openings. In this picture, the interstellar visitor resembles a compact world riddled with caverns and channels, its visible crust only the boundary of a more intricate interior. If instead Atlas III has already begun to fragment, the jets might arise from more than one body, each contributing its own share of outflow. A compact cluster of small nuclei could collectively sustain large structures, even if each piece were losing mass more moderately. The lack of clearly separated condensations in most images argues against a widely spread swarm, yet limited resolution leaves room for a handful of fragments separated by distances too small to resolve. From afar, such an arrangement would still appear as a single source with complex internal geometry. Another possibility envisions a partially hollowed nucleus, its outer shell enclosing interior voids where gas can accumulate as sunlight penetrates deeper through low conductivity material. Pockets of volatile ice may sublimate in enclosed spaces, raising pressure. Weak regions in the shell then give way, opening vents that connect the interior directly to space. Gas rushing outward through these conduits can reach higher speeds than surface sublimation alone, and dust entrained in such flows would emerge as tight jets shaped at first by the channels before the solar environment begins to bend and disperse them. Each scenario carries implications for the fate of the object. A strong, nearly monolithic nucleus might survive many such episodes if it remained bound to the sun, losing only surface layers at each passage. A fragile aggregate or hollow shell, by contrast, could be close to disintegration, its present outburst, perhaps the prelude to eventual breakup as internal supports weaken. For Atlas III, the hyperbolic trajectory ensures that there will be no second visit. Whatever interior story is unfolding must do so within this single brief encounter with strong solar heating. Indirect clues appear in the detailed behavior of the jets. Their steadiness over many rotations suggests that the active regions feeding them stay fixed in position relative to the nucleus rather than wandering across the surface. This stability is easier to reconcile with a small number of persistent vents in a mostly intact body than with a rapidly changing field of debris. Photometric studies of the inner coma hint at periodic modulations in brightness consistent with a rotation period that carries the jets in and out of the line of sight. Observers search for subtle signatures of multiple nuclei, such as slight elongation in the central condensation that might betray more than one core. In some high-contrast images, the inner region appears fractionally extended along one axis, a feature that could reflect overlapping jets, an unresolved pair of fragments, or simply the scattering pattern of dust close to the vents. The interpretation remains ambiguous, limited by resolution and by the smoothing effect of the surrounding coma. Without a spacecraft nearby, the exact number and arrangement of solid bodies inside the luminous knot remain matters of careful inference rather than direct observation. Thermal models help connect surface behavior to possible interiors by tracking how heat from the sun propagates into the nucleus as a function of time and depth. Researchers explore the delayed activation of subsurface regions. Low conductivity can produce lags between changes in solar flux and the onset of strong outgassing. In some simulations, heat fronts converge within a non-spherical body, focusing in zones where fractures intersect that then become sites of enhanced activity and dominant jets. For all this work, a range of configurations remains possible. The data rule out extremes such as a completely uniform isotropically active surface or a widely dispersed swarm of large fragments, yet they do not single out one definitive picture. Instead, they outline a family of interiors bounded by the need to support sustained directed jets without immediate structural failure. Within that family, Atlas III may be a mostly solid core incised by deep channels, a partially hollow shell reinforced by stronger ridges, or a compact cluster of fragments locked together in mutual orbit. In the end, the inner architecture of Atlas III stays hidden. The interstellar visitor reveals itself through light and motion, through the reach of its jets and the subtle shifts in its path, but not through direct images of its heart. Proposals about pieces, caverns, or a single core remain carefully phrased, grounded in the evidence yet open to revision. The unseen nucleus continues to serve as both anchor and mystery, a small dark shape turning silently at the center of its own luminous web. As measurements accumulate, the numbers associated with Atlas III begin to take on a character of their own. They are not merely values in tables, but markers of how far this interstellar visitor stretches familiar categories. Each new estimate of mass activity and probability adds another quiet weight to the sense that this object sits near the edge of what earlier models would have considered likely. Mass is one of the most fundamental of these quantities, yet it remains indirect. No spacecraft flies alongside Atlas III to weigh it by direct gravitational pull. Instead, mass must be inferred from luminosity, from non-gravitational accelerations, and from assumptions about density and reflectivity. Early on, brightness suggested a nucleus perhaps a few kilometers across, similar to some well-known comets. As the jets lengthen and mass loss estimates grow, those initial pictures are revisited. To sustain tens of billions of tons of outflow over months without simply disappearing, the nucleus must either be much denser, much larger, or both. Researchers explored different combinations. If Atlas III carries a low density typical of porous cometary material, then a nucleus at least several kilometers in diameter is needed to match the observed mass loss without catastrophic disintegration. At higher densities, the required size decreases somewhat, but still remains in the realm of multi-kilometer bodies. In either case, the inference is similar. This visitor belongs among the more massive examples of its kind, not a minor fragment but a substantial world on a small scale arriving from between the stars. Set beside earlier interstellar objects, the contrast is striking. One of them, traced only briefly during a passing visit, appears to have been compact and relatively light, its estimated mass many orders of magnitude smaller than that now proposed for Atlas III. Another, more obviously cometary, falls somewhere in between. Within a sample of only a few, Atlas III stands out as a massive outlier, a data point at the far end of the possible range. Statisticians note that with so few examples, any new member can dramatically reshape apparent distributions, yet the mere presence of such an extreme case encourages a reconsideration of prior expectations. Attention then turns to frequency. Given the sensitivity and duration of current surveys, models ask how often an interstellar body of this size and brightness should be detected passing through the inner solar system. If most of the mass in interstellar debris is tied up in large bodies like Atlas III, then such visitors may be rare in number but not unexpected in the time span of modern observations. If, however, mass is spread across many sizes more evenly, then a giant interstellar comet encountered so early in systematic searches may appear disproportionately fortunate. These questions lead to quiet debates in seminars and working groups. Some researchers propose that planetary systems undergoing early stages of evolution may eject many large bodies into interstellar space, seeding the galaxy with a population of massive wanderers. Others suggest that observational biases favor the detection of such objects because smaller interstellar fragments may simply pass unseen, too faint and fast to be caught by existing surveys. In that view, Atlas III might not be an exception at all, but rather the first visible representative of a class that dominates the unseen population. Geometry adds further threads to the pattern. The near alignment of Atlas III's orbit with the ecliptic plane, combined with its retrograde motion, produces a configuration that seems finely tuned from the perspective of observers on Earth. The inclination lies within a few degrees of the planetary plane, maximizing the time the object spends in regions where telescopes already monitor the sky intensively. At the same time, the retrograde direction ensures that its relative speed with respect to the planets is high, a combination that shapes both its observability and its interaction with the surrounding dust and gas. Statistical analyses consider how often such an orbit would arise by chance if interstellar objects approach from random directions. The answer depends on the assumptions, but the probabilities are not large. The alignment is not impossible, merely uncommon, a case where a curve drawn through three-dimensional space happens to pass near a privileged plane. When combined with the object's apparent mass and extraordinary jet structures, this near coplanarity becomes another small contribution to the overall sense that Atlas III occupies a special place among the limited set of known interstellar travelers. Into this landscape of numbers step efforts to quantify how surprising the ensemble truly is. Some calculations treat the mass, orbit, and activity level as independent variables, each with its own probability distribution, based on limited data and on theoretical models of planet formation and ejection. The combined likelihood of drawing an object with the observed combination of properties from such distributions can be low, a quiet reminder that nature sometimes produces rare configurations that nonetheless occur without needing any cause beyond chance and familiar physics. Other perspectives suggest that the probabilities themselves may be incomplete. If current surveys have only begun to map the true variety of interstellar debris, then the current estimates of what is likely may be strongly shaped by the very few objects seen so far. In that case, Atlas III does not violate an established norm, it helps to define that norm. Once more interstellar bodies are discovered, the appearance of a large, strongly active visitor may seem less extraordinary in retrospect than it does now at the beginning of systematic exploration. Throughout these discussions, voices from adjacent fields bring complementary insights. Planet formation theorists recall that young planetary systems can eject vast numbers of icy bodies into interstellar space, especially when giant planets migrate or scatter. Galactic dynamicists note that over billions of years, the orbits of such fragments mix throughout the stellar neighborhood, creating a diffuse background of potential visitors. In such a context, an object like Atlas III becomes a natural consequence of the long, slow churn of planetary birth and loss across many stars, even if the exact combination of its properties remains rare. A smaller group of researchers entertains more speculative interpretations. They consider whether some fraction of interstellar objects might be shaped not only by natural processes, but also by technological activity in the same way that human probes are now leaving the solar system to drift among the stars. In this view, probabilities derived under the assumption of purely natural origins may not capture the full range of possibilities. These ideas are presented with careful language as hypotheses to be tested rather than conclusions, and are weighed against the many ways in which conventional physics can already explain most features of Atlas III's behavior. In the end, the numbers that initially seem to strain belief settle into a more measured place. They remain large, unusual, and instructive, yet they no longer stand alone. Each is linked to a chain of reasoning, to uncertainties, and to the recognition that early samples can mislead as easily as they illuminate. Atlas III teaches that interstellar visitors can be massive, energetically active, and geometrically well aligned with planetary planes, and that such combinations, while perhaps uncommon, are part of the broader tapestry of what icy bodies can be when lifted from their home systems and sent wandering through the galaxy. Far from the bright inner regions where Atlas III shows its sweeping jets, other instruments keep watch from the cold outskirts of the solar system. Around Jupiter and beyond, spacecraft move along their own carefully planned paths, carrying detectors that are tuned not only to the planets and moons they were built to study, but also to the faint streams of particles and fields that flow through interplanetary space. These quiet witnesses are distant from the interstellar visitor, yet still close enough that their sensors can register subtle traces of its passage. One spacecraft loops again and again through the domain of Jupiter, diving in toward the giant planet and then arcing back out along elongated paths. Its primary task is to investigate the deep interior, the belts of radiation, and the complex magnetic environment of that world. On board, however, are instruments that measure charged particles, dust impacts, and the fine structure of the solar wind. As Atlas III moves outward along its hyperbolic path, there comes a time when the visitor's projected trajectory passes within tens of millions of kilometers of the region traced by this mission's orbit. From that distance, no camera can resolve the nucleus or the delicate geometry of the jets. The interstellar traveler is only a point fainter than most of the moons that circle the planet. Yet the streams of gas and dust that once formed long beams near perihelion now continue expanding into surrounding space, thinning and dispersing as they go. The spacecraft's detectors, sensitive to small changes in particle populations and directions, stand a chance of sampling material that has at some earlier time flowed outward from Atlas III. Controllers on the ground adjust observation plans to make use of this coincidence. They cannot steer the spacecraft directly toward the visitor, but they can time certain measurements so that they occur when models suggest the path of the diluted jets may intersect the spacecraft's own environment. Instruments that normally monitor the general solar wind and the ambient dust environment are set to higher sampling rates. Data downlink schedules are refined to ensure that any unusual signatures recorded during this interval are transmitted promptly and preserved in full resolution. As the days pass, the spacecraft continues its motion through Jupiter's extended magnetosphere and into regions more directly shaped by the Sun. The interstellar visitor farther away travels along its outbound arc, its activity now declining as solar heating diminishes. The once narrow jets broaden and lose definition, becoming part of a more typical dust and gas tail that stretches behind the nucleus. Whatever particles eventually reach the realm of Jupiter do so as part of a diffuse cloud, mixed with the ever-present background of solar wind ions, electrons, and native dust. When the relevant interval ends, analysts sift through the recorded data. They look for small deviations from the usual patterns, a slight change in the direction from which dust grains appear to arrive, a temporary enhancement in certain molecular ions, or a shift in the fine structure of the magnetic field that might hint at a passing stream with a different history. The signatures are subtle at best, and any possible association with Atlas III remains carefully phrased. Nevertheless, the very act of searching extends the influence of the interstellar visitor into the outer system, linking it to instruments that orbit a world far removed from the bright inner stage where the jets first drew attention. Beyond Jupiter, another spacecraft cruises on a long journey toward the system of icy moons around a more distant giant planet. Its trajectory set years earlier happens to bring it within a broad swath of space through which Atlas III's tail will later pass. The spacecraft carries cameras, spectrometers, and particle detectors designed to study the surfaces and environments of frozen satellites, but along the way it samples the general interplanetary medium. For a time, its path and that of the interstellar visitor form a loose three-dimensional crossing within the immense volume of the outer solar system. Here, too, any encounter is a meeting of fields and particles rather than of resolved shapes. The spacecraft does not turn visibly toward the distant nucleus, but it continues to record the charged particles and dust grains that strike its sensors. If a tiny fraction of these particles once belonged to the outflows of Atlas III, they arrive as anonymous members of a larger flow, their origin inferred only through careful cross-comparison of timing, direction, and composition with models of the dispersing tail. Closer to the edge of the heliosphere, still other spacecraft drift on paths that will eventually carry them beyond the Sun's protective bubble altogether. Their instruments, once focused on the planets and rings closer in, now mostly track the intensity of cosmic rays, the structure of the heliospheric boundary, and the changing influence of the solar cycle. Atlas III remains far inside their orbits, a bright event occurring in a region that these aging probes can no longer observe directly. Even so, the interstellar visitor shares with them the broader context of motion between stars as both cometary nuclei and human-made vessels follow trajectories that bridge the space between planetary systems. Taken together, these distant watchers underline a shift in how the solar system is observed. The passage of Atlas III is tracked not only from the surface of Earth and from Earth orbit, but also from vantage points scattered across many astronomical units of distance. Some perspectives come from planned campaigns, others from serendipitous alignments between long-established spacecraft and the path of a newly discovered visitor. Each instrument provides a different piece, whether an image, a spectrum, or a chart of particle flux and magnetic direction. In most cases, the traces of Atlas III in outer system data are faint or ambiguous, easily overshadowed by the dominant patterns of solar wind, planetary fields, and background dust. Yet the effort to identify them is significant in itself. It shows that interstellar visitors are now studied within a three-dimensional observational lattice, one that includes both dedicated astronomical observatories and exploratory spacecraft whose original mandates lay elsewhere. The solar system has become in this sense a networked environment where a single passing object can touch many sensors spread across great distances. As Atlas III continues outward, the role of these deep space witnesses evolves from opportunistic sampling to archival context. Their measurements of the heliospheric environment through which the visitor travels help to define the conditions that its tail encounters as it stretches and thins. When researchers later reconstruct the full story of the jets, the non-gravitational forces and the fading outburst, they can embed their models in a background calibrated by these distant probes. The interstellar comet and the scattered spacecraft thus share a common frame, each contributing to a wider understanding of how material flows through the space carved out by the Sun within the broader galaxy. As Atlas III drifts outward along its long one-time arc through the solar system, thoughts in observatories and planning meetings turn toward the future. The interstellar visitor has shown what can happen when an object from another star system passes close to the Sun, while a growing network of instruments watches from many vantage points. Yet even with all that has been learned, large gaps remain. Some arose from geometric constraints, others from the limits of current facilities, and still others from interruptions in the flow of data. The next visitors, when they come, will arrive in a landscape of instruments that is changing in response to experiences like this one. On a high desert plateau in the southern hemisphere, a wide-field telescope of unusual power nears completion. Its large fast mirror and enormous camera are designed to scan nearly the entire visible sky every few nights, gathering repeated images that chart how things change over time. This facility, once fully operational, will transform the search for transient and moving objects. Small asteroids, distant supernovae, variable stars, and interstellar comets will all leave their traces in its nightly surveys. The era when only a few instruments could detect faint moving specks like Atlas III will give way to a more systematic, deeper watch. In such a survey, interstellar visitors may stand out more clearly. Their incoming speeds and directions differ from bodies loosely bound to the Sun, and the repeated imaging cadence will catch them earlier in their inward journeys. Where Atlas III emerged into broad awareness after it had already approached the realm of the giant planets, future visitors may be recognized while still far beyond, allowing more time to plan detailed follow-up. Observation campaigns that had to compress months of work into the weeks around perihelion could instead unfold more deliberately, starting while activity is still minimal and continuing through the onset of jets and any outbursts. Alongside these large all-sky instruments, more specialized projects focus on the possibility that some interstellar objects might carry technological signatures. Arrays of modest telescopes, carefully arranged and automated, watch for unusual tracks in the sky and for objects that behave in ways not easily explained by simple reflection or sublimation. Their cameras and sensors are tuned to capture fast motion, high angular resolution, and spectral detail. The logic is straightforward. If humanity now sends probes beyond the heliosphere, then other civilizations, if they exist, might have done so as well, leaving behind artifacts that drift through the same galactic environment as natural debris. The passage of Atlas III provides a kind of rehearsal for these efforts. Its remarkable jets, non-gravitational accelerations, and unusual orbit have forced models to stretch, but they remain within the bounds of known physics. In doing so, they help to define what a highly active natural object can look like and how it can move. Future visitors that differ from this expanded template will stand out more sharply. Unusual light curves, anomalous spectra, or motion that cannot be reconciled with any realistic combination of outgassing and rotation will have to be evaluated in light of the lessons learned from interstellar comets like this one. Space missions, too, are being conceived with interstellar targets in mind. Concepts for rapid response spacecraft capable of launching on short notice and intercepting incoming objects discovered by next-generation surveys are being studied. Such missions would carry cameras, spectrometers, and dust analyzers designed to operate at high relative speeds, perhaps tens of kilometers per second during brief flybys. The goal is to close the observational distance that now separates Earth-based telescopes from the nuclei of interstellar visitors, and to see directly the source regions of jets, the textures of surfaces, and the fine structures of Comet. In parallel, slower, more deliberate missions are envisioned that might rendezvous with a future interstellar object whose trajectory allows. If a visitor is discovered early enough and follows a path that can be matched by a spacecraft with efficient propulsion, then a close extended inspection becomes possible. Instruments could watch the development of activity from a vantage point nearby, resolving individual vents, monitoring rotation, and measuring non-gravitational accelerations from within the coma itself. In such a scenario, the questions about internal structure fragmentation and jet origins that remain open for Atlas III might find clearer answers. The development of these missions depends on technologies that are advancing step by step, more capable propulsion systems, lighter but more sensitive instruments, and faster data processing. Ground-based work on Atlas III feeds directly into their design. The unexpected lengths of the jets, the high mass loss rates, and the complex interactions with the solar wind all become boundary conditions. Engineers and scientists planning future spacecraft must consider that an interstellar comet can be both more active and more structurally intricate than many local examples, and that instruments will need dynamic ranges and response times suited to such extremes. On the ground, improved coordination frameworks are taking shape. The networks that share alerts about near-Earth objects and interstellar discoveries are refining their communication channels and data formats. When the next interstellar visitor appears, messages will move quickly between survey teams, orbital calculators, spectroscopists, and mission planners. The experience of tracking Atlas III with its brief periods of visibility and its rapid changes near perihelion has underscored how important it is to distribute responsibilities across the global community so that no single observatory's weather local conditions or institutional challenges can leave unfillable gaps. Educational and public engagement efforts also evolve in light of such events. The passage of Atlas III has shown that the story of an interstellar visitor can capture imagination while still being told in careful, measured language. Future campaigns may integrate citizen observers more directly, providing ephemerides and observing guides that allow small telescopes to contribute to light curves and imaging. The line between professional and amateur data can blur in useful ways, especially when many eyes across the world are needed to follow an object through different time zones and viewing conditions. All of these strands, the large survey telescopes, the specialized monitoring arrays, the prospective spacecraft, and the coordination frameworks converge on a simple idea. The solar system is not an isolated domain, but an open stage through which material from other stars occasionally passes. Each visitor, whether quiet or spectacular, carries information about its place of origin and about the processes that shape planetary systems throughout the galaxy. Atlas III has demonstrated how much can be inferred from careful observation even at great distances, and how much remains beyond reach without closer inspection. As the interstellar comet recedes, growing fainter and smaller in images taken from Earth, the instruments being prepared for the future quietly approach readiness. Mirrors are aligned, cameras calibrated, detectors cooled, and software tested. On drawing boards and in simulation environments, trajectories for hypothetical missions are refined. The next object from another star system may arrive with little warning or with ample notice, may be calm or active, small or massive. Whatever its nature, it will encounter a solar system now more aware of such visitors, equipped with new eyes that have been shaped in part by the fleeting luminous passage of Atlas III. As the weeks lengthen and the calendar turns toward colder seasons in many observing sites, Atlas III continues along its outward leg. The hyperbolic path that once brought it inward toward the sun now carries it steadily away, the curve flattening into something that again resembles a near straight line when plotted over large distances. The visitor that once dominated observing plans now occupies a smaller place in nightly schedules, one target among many, its brightness diminishing as both solar illumination and proximity to Earth decrease. The jets once so sharp and extended grow softer. Their outer reaches have already begun to fray into the general background of interplanetary dust, and their inner portions shorten as activity at the nucleus declines. Images taken with the same instruments that once recorded beams many millions of kilometers long now show more modest structures, a coma that gradually becomes more symmetric, and only faint hints of the extraordinary geometry that defined the weeks around perihelion. The transition is neither sudden nor uniform, but a steady easing toward a quieter state. Spectroscopic signatures change as well. Gas lines that grew strong when buried ices were newly exposed begin to weaken, some fading into the detection limits of even the largest telescopes. Ratios between different volatile species drift toward values more typical of comets that are leaving the inner solar system behind. Dust continues to scatter sunlight, but the total flux from the coma and residual tail declines. In long-term monitoring plots, curves of brightness versus time bend downward, tracing the end of the outburst in smooth descending arcs. In data archives, however, the peak remains fixed. Images from the days and weeks after conjunction, when the jets were at their greatest extent, already sit beside earlier frames in which Atlas III was a nearly ordinary interstellar comet, and later ones that show its gradual fading. The story of its activity is now encapsulated in these records: a quiet approach, a hidden transformation near the sun, a brief period of extreme jetting, and a slow return toward relative calm. Analysts move more often between historical and current data, using the full sequence to test and refine their models. Orbit solutions extend farther into the future. With non-gravitational parameters constrained by months of post-perihelion astrometry, predictions of the outbound track become more secure. Integration forward in time shows the visitor climbing outward through the realm of the giant planets, then passing beyond, eventually crossing the boundary where the solar wind gives way to the interstellar medium. Beyond that region, the sun becomes once more just one star among many, its influence reduced to a slight deflection in a path that stretches into the galactic background. In offices and conference halls, attention gradually shifts from nightly logistics to synthesis. Papers collect and compare results from different teams: imaging, spectroscopy, polarimetry, dust modeling, and dynamical studies. Each contributes a piece of the puzzle, and where they overlap, a picture emerges of an interstellar nucleus that carried deep volatile reservoirs, complex internal structure, and a spin and orbit geometry that combine to draw out jets of remarkable length. Points of agreement strengthen confidence in some aspects of the interpretation, while discrepancies mark areas where understanding remains incomplete. Several themes recur in these discussions. One is the nature of the vents that produced the jets, how deep they reached, how they opened, and how stable they remained over time. Another is the internal architecture of the nucleus, including whether it was largely solid, partially hollow, or gently fragmented. A third concerns the statistics of interstellar visitors in general and how Atlas III's mass, orbit, and activity influence estimates of how many similar objects may pass through the inner solar system over long spans of time. Each theme links detailed measurements to broader patterns in planetary science and galactic dynamics. Alongside these concrete questions lies a quieter reflection on perspective. Atlas III has been observed from a planet whose inhabitants have only recently begun to recognize that interstellar objects pass through their system at all. For most of the solar system's history, visitors like this one came and went unseen, their jets unfolding and fading without record. Now, with coordinated surveys and instruments spread from Earth orbit to the outer planets, a single interstellar comet can be followed through much of its journey, turning what would once have been a silent event into a carefully documented episode in the scientific record. The object itself, however, remains indifferent to this attention. It continues to spin, to cool, and to drift outward its remaining ices, gradually returning to the temperature of deep space. Dust left behind along its path forms a tenuous trail that will slowly disperse under the combined influence of radiation pressure collisions and gravitational perturbations. If other planetary systems lie along its future route, their own distant inhabitants may someday detect a faint, fast-moving comet in their skies, unaware that it once flared into extraordinary activity near a different star called the Sun. In the end, Atlas III leaves behind more questions than answers, yet the balance has shifted. Where there was once only the knowledge that an interstellar object had been found, there is now a detailed record of how such a body can behave under strong solar heating. The visitor has demonstrated that jets can reach scales far larger than previously documented, that mass loss can be intense yet sustained, and that non-gravitational forces can subtly reshape a hyperbolic path without compromising its overall coherence. It has also shown how human instruments and institutions respond to such an event, revealing strengths, limitations, and opportunities for future encounters. As the interstellar comet grows fainter and eventually slips beyond the range of practical observation, it returns to a form of invisibility, a dark fragment moving among the stars. Yet in data centers, on storage media, and in the minds of those who studied it, a different kind of presence persists. The light it reflected and emitted has been captured, counted, and shaped into understanding. Atlas III is no longer just a transient point of brightness. It has become a reference case, a quiet standard by which future visitors will be compared, and a reminder that the space between stars is not empty but threaded with objects whose brief appearances near suns can reveal deep stories about the workings of planetary systems throughout the galaxy.